Okay, so the one thing that we did not get to in class yesterday with regards to our significance tests is a one sample t-test about a claim made about a population mean. So you can see here that our targets are to be able to understand how to check the conditions for carrying out a test about a population mean. We're going to find they're very much the same as they were for a confidence interval. We want to be able to conduct the whole test about a population mean. We already know how to construct a confidence interval for a population mean, and we're going to be practicing tomorrow. I've made another video on how we do a significance test or hypothesis test for matched pairs experiments or paired data. But the one that I want to look at here is this one with regards to the level of dissolved oxygen in a stream of river, which you'll find in your set of examples. It says the level of dissolved oxygen in a stream or river, is an important indicator of the water's ability to support aquatic life. A researcher measures the DO at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. A dissolved oxygen level below 5 milligrams puts aquatic life at risk. Does the data provide evidence that the aquatic lives are at risk? So we know, of course, that the word evidence means that we need to carry out a test of significance. So I'm going to do so. But I do notice that this is not about proportions, but it's rather going to be about taking these measurements and calculating a mean. Hence, this is going to be a t-test. So what I'm going to do first is I put these values in a list in my calculator, and so we'll pause this recording a moment to give you time to put these numbers in list 1 of your calculator and to get your one variable statistics. Okay, I've put these numbers in my calculator. I've got my one variable statistics. I'm ready to start my hypothesis test. So the question is, there's a claim that's made about the mean. And it says here that a dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. So we want to see if we have evidence to say there is below 5 milligrams per liter. So this is going to be in our alternative hypothesis. Our alternative hypothesis always has the inequality in it. The null hypothesis then is going to have the equality, so we're going to say that mu is equal to 5 milligrams. So for the HO, mu is equal to 5 milligrams. And for the HA, mu is less than 5 milligrams per liter. Now in the HO, we actually could say in this case that mu is greater than or equal to 5 milligrams. But typically you'll find that they use an equal sign with the null. So now I need to define the variable that I've used. And so unlike proportions, I'm not going to define p because I'm not using p. I'm going to define mu. And mu is always defined as an average. So it is the average DO in all possible samples that could be taken from this river. So the average DO in the entire river, I'll say. I have to make it clear that it is a population value that I am defining. River or stream. So the average DO in the entire river or streams, because it is rivers or streams, right? Yep, it's just one river or stream. That's a little bit goofy. Okay, So we've defined mu. Now, we also like to list our statistics that we're going to need when we calculate, when we get to our do. So I'm going to go and get my statistics for list 1, and there's my x bar, 4.77, and I see my s is 0.9396. So I'm going to list those as well. I've got an x bar equal to 4.77, and I have an s equal to 0.9396. Those are all my necessary statistics, other than n, of course, which is 15. So my state is complete. Now, we learned when we did confidence intervals to estimate a population mean, we learned that our conditions are random, normal, and independent. They are going to be here as well. So was I told that they were selected at 15 random places? Yes, I was. So random, check. Now with normal, we need a sample size we know for means that's at least 30, and if it's not 30, we need to look for skewness or outliers in our sample. So I'm going to make a graph of the data that I have stored in my calculator. Second y equals, go to plot 1, and I want to make sure that it's on, that the histogram type is selected, and that my X list is list 1. If so, I'm going to zoom 9. Oh, good. I don't see any skewness. I don't see any outliers, but I have to provide evidence that I actually checked this. So I'm going to draw a little sketch. Again, don't have to be perfect, or doesn't have to be perfect, but should give us an idea, or give proof that we did in fact check this distribution. That looks like it. And so I'm going to say that because I don't see any strong skewness or outliers, normal is satisfied. Now I'm going to pause this recording just in case it's going too long and do the do and the conclusion in a separate video.